Do you remember the fact that force is a vector quantity, not scalar, and it would give you a direction? How can we get to this? Charge is scalar, but electric field is vector, so resultant would be vector. Okay, I think so that you are aware of the fact that if you multiply any scalar number by any vector, then the resultant would be vector only. Just it's a multiple of this. So this was all. We can even make it more fun. We can say that since charge are quantized, and since q is just an integral multiple of electronic charge. This is just a fun way. I just noticed it. So then we can now move on to electric fields. So now we get to electric field. Now electric fields are just we use this formula to explain electric field. Consider this is electric field, this is q, and this is f. If we just bring q in division in LHS, if we just move q in LHS, then it would give you electric field. F by q is equal to electric field. Now just for this, for getting electric field, what we can say that force on any charge divided by the charge itself will give you electric field. But what does electric field actually means? Electric field means that if you apply a force on any charge, if a charge q gets a force applied on it due to electric field. Now electric field is the force on a unit charge, unit 1 coulomb charge, 1 positive coulomb of charge. The force which is experienced by 1 positive coulomb of charge is called electric field. Okay, so that's why when you multiply it by q, this q factor, then it finally gives you the charge of this much coulomb of charge. Are you getting? This is charge on, this is force experienced by plus 1 coulomb. This is whatever charge we are having. If you just multiplied, then finally we could get the force on whatever charge value this is. This is basically electric field. We can even get it in the NCERT way. What does electric field actually signify? Electric field, here is it. I think so that you are able to see it. Electric field at a point in the space around a system of charges tells you the force on a unit positive test charge would experience if placed at that point without disturbing the system. Okay, you're just telling us that if we have placed any charge unit 1 coulomb of charge, then obviously 1 coulomb, as I told you, is so large. Is I told you na that 10 to the power 18 concept. It's so large that it would cause other particles surrounding it to displace. So that's why NCERT tells us the safer way that use this formula, put a very small 0.00000000001 whatever infinitely small coulomb of charge, and find the force on that and just divide it so that we could get the charge on 1 coulomb. Okay, by this method we can actually get this. Okay, so but in the definition you would never write this test charge concept. This infinitely small charge is called test charge, and we will never write it in the definition. In the exact definition we would always write the force. Electric field is nothing, it's just force. But SI unit is not Newton and dyne here. Here the units are not Newton and dyne because it's the force per unit coulomb. Okay, are you getting? The SI unit is Newton per coulomb. The force experienced by unit coulomb of charge is called electric field, and it's having a mathematical formula as well. This is the mathematical formula. F by Q is E is equal to F by Q. Force on Q divide force on, more appropriately just write F by Q naught. Q naught is used to show test charge, and always make a habit that once you write the formula, mathematical formula, just write what are the variables referring to. Here where E is equal to electric field, force F is equal to force on test charge, and Q naught is equal to charge on test charge. This final division would give us what? This final division would give us the force experienced by unit coulomb of charge. This is an indirect way to find unit force on unit coulomb of charge. Now talking of unit, SI unit, I told you it's just a rate at which by changing the charge you could get the force. So it's Newton per coulomb. Okay, it's Newton per coulomb, and here is dyne per coulomb. In CGS there is coulomb, there is stat coulomb as well, and there is F coulomb as well. These both are CGS units of charge. Sorry, of electric field. Electric field are denoted by E, capital E. They are vector quantity, not scalar. They are vectors. Okay, they do have direction. That's why once you get this force, when you multiply it by some scalar number, finally you get force, which is a vector. Okay, this is electric field for you, explained in short. No man, this topic of electric flux is tough. Hey, wait, I went here wrong. Electric field, with electric field, I wrote SI unit is what? Newton per coulomb. Yes, right? Yeah, it's right. Oh, sorry. The definition, the following definition is just, you would get fascinated. It's tough, very tough, and it gets even more tough if you try to look into its actual essence. Okay, so before starting the definition part, I would just go to the mathematical expression, because this is not what scientists wanted to define something. They were just physicists were trying to find out. Okay. Anyway, electric flux is denoted by phi. Phi, and this phi is equal to integration of electric field per area with respect to area vector dot product here. Okay, no, just go, let's go bit by bit. This is flux, and it's a scalar quantity. This is electric field, it's vector. Area, yeah, area is also vector quantity. I will tell you how. But area is also vector, and this is electric field is also vector. The only way to get a vector to convert to multiplication of two vectors can be vector as well and can be scalar as well. We will be doing dot product. Dot product means it depends on cos theta, the angle between this electric field and area vector. It would depend on the cos function of that angle. Okay, and then finally we have to, after doing all this thing, we have to close integrate this much of thing to convert this vector product into this scalar quantity called flux. Now let's try to understand bit by bit more. Area is a vector quantity. If you don't know, if you didn't knew, uh, why would you even try to know? Because we are usually into the thing that area is scalar, and don't worry, area is vector only here. At all other places you would consider area as scalar, but the physics, it's physics. And also you have to remember that the area which we are used to in mathematics, they just ask for uh, they just give you length, they just give you breadth, and then ask you area. If did they ever give you length in form of vector? No. Did they ever give you width in form of vector? No. Then why can you? How can you even give answer in area vector for the finding of area? But in physics, in this is length. Length is a vector. No, length is a vector, but it depends. Length is a vector, but it depends. Are you talking of displacement or distance? Anyways, just don't uh, get into much of it. This is area, and consider it in a plane, xy plane. Here I just why did I even draw it? It's more of like a rhombus. Consider this surface in xy plane, and the area vector points in a direction moving outward of this plane, outward or inward, either dot or either cross. Okay, outward means this dot, inward means cross. uh, yes, so area vector points, this is 3D diagram, and area vector points just perpendicular to the plane. Okay, it points perpendicular to the plane. For a surface, if water is flowing, for example, consider a pipe. Okay, I'm seeing if I could there is some pipe or something like that. Consider pipe, water is flowing, flux is this flow. We want to know that how much water is flowing in this pipe. Consider if the water is flowing perpendicular to the pipe, what will happen? No flow of water. For example, this pipe is leaking at some point here. The flow would get reduced, okay, and lesser water will come in this because much of water is wasted because of the leakage problem. Okay, so the amount of water which would be getting into this surface would tell us the flow. Similarly, flux tells us the flow of electric field into area. Okay, the flow of electric field into small units of area which are integrated to get the final flux for the surface. Okay, it's more appropriately if we would write flux for the surface or for the area as a whole is given by this. Now for dot product I told you it's just because of to get this vector into scalar because we wanted flux to be scalar. Furthermore, dot product will give you cos theta. Now just listen, it's very important to be learned properly. This is the a surface in which I want water. I want to know how much water is flowing. Currently, there is a totally fine condition of pipe ahead and water flows in this direction. So the maximum water would flow. If there is a leakage problem at somewhere before reaching this level, if there is some leakage there, then water flow would reduce. Okay, now the direction of water flow is here and the surface is in this direction. How can we know the direction of surface? Now just remember this surface is an area. Its area vector would point in this direction or in this direction. Okay, it would point outward. So the area vector from this surface would point outward. Consider this surface. This is pipe. Area vector is pointing outward. Okay. Now area vector is pointing outward. We want to know the water being flowing. Water. Oh wait. Water is flowing in this direction. So it would be better if you assume the area vector to be in this direction. Sorry. Area vector is basically the vector. It can be drawn in both the directions, either directions. This one, it can be, as I told you, it can be drawn outward as well as inward. If it would be drawn outward, it could also be drawn inward, but basically consider a cube. Now this is a cube, whatever. So if here I went wrong, so anyways, please understand. The area vector of this surface could even go in positive z-axis and negative z-axis, but this is a cube. I do have a Rubik's cube. Let me bring it. I couldn't find it at the spot where I thought. काम का time भी नहीं मिलता. Anyways, consider this surface, this particular surface. Now there can be two area vectors, one pointing in this direction and one pointing inward of this cube. Okay, If you can again imagine, uh, at least rubber should be there. I could get sharpener here. So this surface could have two area vectors. Area vector is always perpendicular. It could have area vector just outward of z-axis and one going inward, and the inward going would go inside this cube. Well, it's not cube, it's cuboid. Okay, it's applicable for all the surfaces. It can be spherical also, but we always consider area vector to be moving outward. So instead of uh, giving an area vector inward, we would just ditch this and we would consider an area vector outward. Okay, so for sphere also we have an area vector outward, moving outward. Just draw a perpendicular, a normal outward. This would be the area vector for this particular very small portion of surface. Anyways, here in that pipe example, since the water is moving in this way, uh, the outward way for this surface is not having, is not any closed uh, 3D surface, not having any boundary. So even this is an area vector and this one is also an area vector, but taking this as area vector is more convenient because water would be moving outward from this direction. Okay, now the water is moving, and consider this is case one, it doesn't leaks anywhere, and once it leaks the flow of water would get reduced. But anyway, the flow of water will be in this direction. Okay, the flow of water is in this direction, and such that the angle, now you can you find the angle? Can you find the angle? See, area vector in this direction, water moving also in this direction, angle should be 0 degree. Why angle should be 0 degree? See, these two vectors overlap, angle are 0 degree, it can't be drawn. Okay, it's 0. What's the angle here? It's from it, if consider this is some angle, it reduce it till this vector overlaps over this vector, then what will happen? Angle will reduce to 0. So these two vectors are, since they are parallel, they have theta is equal to 0, and in dot product what we have, what we get cos 0 is equal to 1, and we are just and why did I took this example? Just to confuse you. I think so I confused many people. Just remove this dot sign, and dot sign corresponds to cos theta. So we can remove this and use the remove the vector sign. Just remove this vector sign, and this is the magnitude of electric field. This is the magnitude of area, and this is the angle between them. Finally, flux is this. And for definition, what I told you, water examples are very classic examples to explain the phenomena of electrostatics, because electrostatics is quite boring unit, very boring unit. boring as well as hard also. So for two chapters, this is chapter one, and for second chapter also you would uh, have to झेलना पड़ेगा. Now definition: electric flux. The there is a concept of electric field lines. Okay, this is an area, and I represented you water flowing using many lines. Okay, had you if you had noticed, I used many lines to denote the flow of water. Similarly, to denote the flow of electric fields, we have electric field lines. Okay, so it's not something like if there is 1 Newton per coulomb electric field, then it would give you 10 electric field lines. It would give you 15 electric field lines. There is nothing such. It's just a convention to show the strength of electric field. It's just to compare cases. Okay. For example, if a charge gives this electric field and another charge gives very condensed electric fields, means more electric fields per area. Okay, so it means that this charge must be powerful. We could not tell you that how much electric field is there, but we can if it's given. If it's given that one line corresponds to this much electric field, find electric flux, we can actually, but it's kind of confusing, right? The number of is basically just for quantitative, for studying which one for comparison, which one is weaker and which one is stronger, which one is more dispersing, which one is less, which one is non-uniform, and which one is uniform, equally spaced. Okay, number of electric, what's electric flux? Number of electric field lines passing through a s through an area, through an area or through a surface, through an area or through a surface. It's called electric flux. I think so that I have wasted around 15 minutes to just write this much. Just I found it too confusing. That why a number of electric field lines passing through an area or surface is called electric flux. This was kind of misleading for me. Anyway, I could have given this much of time to Gauss theorem. Just a waste of time. Okay, so let's go on. The unit, important one. Electric field gives you Newton per coulomb, area gives you meter square. It's multiplied and you would get, and cos theta is just a number, no unit, and even no dimension. So these are in multiplication. The final unit would be Newton meter square by coulomb. Okay, Newton meter square by coulomb. This complete one is divided. Let's make sure it's clear and legible and readable. Okay, Newton meter square whole divided by coulomb. and CGS unit. Just make it into dyne, Newton into dyne, meter into centimeter square, and coulomb. Coulomb into either stat coulomb or a coulomb. Yes. Oh, sorry. You were not able to see. I didn't notice. The unit should be Newton. Just I think so. You saw that we multiplied Newton by meter square. How we multiplied? Newton by coulomb into meter square. It's Newton meter square by coulomb. So it's the SI unit. And for CGS, just convert Newton into dyne, meter into centimeter. It's whole square of centimeter. So whole square. Just, just I used this brackets just because the centimeter is comprised of two letters. It may be confusing to some. Stat coulomb. Okay, coulomb into stat coulomb, and coulomb is also in CGS units also has an equivalent of ab coulomb in CGS units. So dyne centimeter square by ab coulomb. Okay, this one is very important. This and even this one is more important. Just do remember because it's the founding of Gauss theorem. Now, just do remember because this would get you to the moon.